Imagine standing beneath a machine so powerful it can lift more than 3,000 tons, the weight of nearly 500 African elephants, without taking a single step. You hear the deep rumble of diesel engines, the groan of tensioned steel cables, and the slow, deliberate movement of a boom stretching higher than a 60-story skyscraper. Think about this. Every movement happens with astonishing precision because one mistake could cost millions of dollars in seconds. Welcome to the extraordinary world of crawler cranes, where raw power meets engineering perfection.
Most people see these giants for only a few moments on a construction site, then drive away without another thought. But here's what nobody tells you. A crawler crane is really a carefully balanced system of thousands of precision-engineered parts working together every second. Every pin, every weld, every hydraulic cylinder, and every strand of steel cable must perform flawlessly while carrying loads heavier than entire passenger airplanes. What happens next surprised even experienced engineers, because building one of these machines begins thousands of miles away from the factory floor.
Imagine following a single crawler crane backward through time. Instead of starting in a factory, our journey leads us to vast iron ore mines carved into the earth, where haul trucks taller than houses crawl across red landscapes carrying hundreds of tons of rock. The steel that will eventually hold skyscrapers in the air begins here, buried beneath millions of years of geological history. And this is where it gets truly extraordinary, because every colossal lift starts as nothing more than ordinary stone hidden beneath your feet. In the next stage of our journey, we'll discover how millions of kilograms of raw minerals from different continents come together to create the specialized steel that gives crawler cranes their incredible strength. You'll see why not all steel is created equal, and why a tiny change in chemistry can determine whether a crane safely lifts thousands of tons, or fails under pressure. The journey has only just begun. Now the real transformation begins. Imagine standing inside a steel fabrication plant where plates weighing more than 30 tons glide across automated roller tables with a deep metallic roar echoing through the building. Massive CNC plasma cutters ignite, unleashing jets of superheated plasma reaching nearly 25,000 degrees Celsius 45,000 degrees Fahrenheit, hot enough to slice through 150mm 6-inch, high-strength steel as if it were cardboard. The smell of hot metal fills the air while showers of brilliant orange sparks race across the factory floor, and every cut must stay accurate within fractions of a millimeter. Think about this. Every piece of steel receives its own digital identity before the first cut even begins. Engineers load three-dimensional CAD models directly into the CNC system, and precision servo motors guide the cutting head at speeds of 2 to 6 meters per minute, adjusting automatically as the steel thickness changes. Laser positioning systems verify alignment within plus or minus 0.2 millimeters, because even a tiny error here could multiply into centimeters by the time the boom reaches over 100 meters into the sky. Most people never think about this, but a crane's future lifting power starts with invisible digital measurements. Once every component leaves the cutting station, giant robotic manipulators rotate sections weighing several tons into place for machining. Towering CNC boring mills spin carbide cutting tools between 150 and 400 revolutions per minute, removing millimeters of steel with every pass while streams of coolant hiss against glowing metal. You hear the steady rhythm of precision cutting, smell warm cutting oil, and watch perfectly curled ribbons of steel collect beneath the machines. Every bearing seat and pin connection must remain within tolerances as tight as plus or minus 0.05 millimeters, thinner than a human hair. But here's where the factory becomes even more extraordinary. The perfectly machined pieces now move toward one of the most demanding stages in heavy engineering, joining enormous sections into a structure strong enough to lift thousands of tons without twisting or cracking. The heat waiting ahead will rival the surface of a volcano, and what happens during welding determines whether this crane earns the right to leave the factory at all. The crawler crane now looks complete, but appearances mean nothing in this factory. Before a single machine can lift its first load, it must prove itself to an army of sensors, robots, and engineers who trust measurements more than their own eyes. Think about this. A crane worth millions of dollars can fail inspection because of a flaw smaller than a grain of sand. This is where engineering stops relying on strength alone and starts demanding absolute precision. Yenst engineers because the computer never gets tired, distracted, or complacent. Imagine a network of high-speed laser scanners sweeping across every weld, pin, and machined surface thousands of times every second. Advanced 3D metrology systems compare the finished crane against its original digital design with tolerances as fine as plus or minus 0.1 millimeters, instantly highlighting even the smallest deviation. AI-powered vision cameras inspect weld beads, paint coverage, bolt placement, and hydraulic routing faster than any human could. What happens next surprised even experts. But lasers only reveal what they can see. Hidden deep inside thick steel joints, ultrasonic testing sends sound waves traveling at nearly 5,900 meters per second through the metal, searching for microscopic cracks or trapped air pockets invisible from the surface. Magnetic particle inspection exposes tiny surface fractures, while critical welds may also undergo radiographic X-ray testing to verify complete penetration. The factory accepts rejection rates of only a few %, because one defective weld could jeopardize an entire lift. Most people never think about this, but even the smartest inspection robots step aside for one final expert. A veteran welding inspector slowly studies the most critical joints, listening to the faint ring of steel under a small inspection hammer and spotting subtle details that algorithms sometimes overlook. Years of experience guide every decision, because instinct built through decades cannot always be programmed. And just ahead, you'll witness the ultimate challenge. The moment this giant finally lifts a crushing test load to prove it belongs on the world's biggest construction sites. Imagine looking down on Earth from space and watching hundreds of crawler cranes rise above skylines, ports, offshore wind farms, and giant industrial projects all at once. These machines quietly power some of humanity's biggest achievements, from nuclear power stations to bridges that span entire bays. The global crawler crane industry now supports a market worth well over $10 billion annually when new equipment, parts, and support services are combined, with thousands of new heavy crawler cranes entering service each year. Think about this. Every one of those giants traces its story back to iron ore buried deep beneath the Earth's surface. Most people never think about this, but just 5 countries dominate much of the world's heavy crane manufacturing and demand. China leads by a wide margin, followed by major producers and users such as Germany, Japan, the United States, and South Korea, each contributing advanced engineering, specialized components, or large-scale construction demand. Together, these nations account for the majority of global crawler crane production and deployment. Their factories compete fiercely to build machines that lift higher, travel farther, and handle heavier loads than ever before. Did you know that today's largest crawler cranes can lift more than 5,000 metric tons, enough to raise entire offshore platform modules in a single operation? Did you know that transporting one of these giants to a job site often requires dozens or even hundreds of truckloads because the boom, counterweights, crawlers, and machinery travel separately? And here's another surprise. Assembling the crane on site can take several days to several weeks before it performs its very first lift. What looks effortless on the finished project actually represents months of planning and logistics. But the next decade promises something even more remarkable. Engineers are developing smarter cranes with AI-assisted lifting systems, real-time structural monitoring, predictive maintenance, hybrid and electric power technologies, and increasingly autonomous setup procedures. The crawler crane of tomorrow won't simply lift heavier loads. It will think faster, operate more efficiently, and help build projects once considered impossible. And in our final chapter, we'll bring this incredible journey full circle, revealing why you'll never look at one of these engineering giants the same way again.